Hello, everyone. So we've talked about areas of parallelograms, triangles, trapezoids, and kites. But polygons are not the only things we will be finding the area of. There are also some things that we've worked with already, and we've talked about the area with Chapter 1, and those objects are circles. So, let's talk about the area of a circle. I am confident that you already are aware of this formula because we've already used this formula, and it's a very common formula. You did it in middle school. We've done it for years. It's area of a circle equals pi times the length of the radius squared. So let's talk about where this comes from. In calculus, you will learn a very, very nice formula, way to derive this formula. And that method to derive it is using integrals, which you do not know yet. And even if you do know it, remember, you don't know anything except for what we've learned in this class, besides the foundational algebra skills that will be needed to complete this work. So, you don't know integrals yet. But that's a great way to prove this. So when you take calculus in the future, when you get to integrals, you will go over a way to show that the area of a circle is equal to pi r squared. Another way to show this is using limits, which unfortunately you also don't know. So, depending when you learn limits, whether it is in pre-calculus or calculus, usually it's pre-calculus, but of course this year I may not get to limits because I don't know if you know this, we have a disease that has kept us at home for a long time, so I may not get to it. But if you do get to it in pre-calculus, or if you get to it in calculus, ask your teacher, hey, can we derive the area of a circle using limits? And you could talk about that. But let's talk about the area of a circle in a very, very broad sense. Imagine that circle's not terrible. We have the center. We have all these points that are equidistant from the center. So we can divide it up into sections. So I'm just going to make a bunch of diameters, about evenly spaced apart. All right, so we have all of these diameters creating these figures, these pieces that are 2 radii and an arc. A figure like that has a name. A region in a circle bounded by 2 radii and an arc is called a sector of a circle. So a sector of a circle is a region bounded by 2 radii and an arc. It is not a wedge. It is not a slice. It is called a sector of a circle in geometry. So I don't need you to use this in like real life terms. So like if you're having pizza and you say, hey, I would like a slice of pizza, that's fine. You don't need to say, I would like a sector of pizza. But in this class, it is a sector of a circle, that figure. Also, pizza's 3-dimensional. Now, we have all of these sectors. We have all of these sectors. Each sector is pretty close to a triangle. So just conceptually, this is not how they really work out. Just conceptually. Let's say we took each of these triangles and we unrolled it. We took each of these triangles and treated each of these arcs as the base of the triangle. So I'm going to take all those triangles and let's straighten out each of those arcs so that that's the base. So we would have a bunch of them. I understand there were more in my circle, but I'm not going to draw however many were there. We just need the concept. And if we wrap these together, these points would all meet up and it would form the circle. Now I understand that in reality, these are not triangles. Those are triangles if you draw the chord, but conceptually think about it like this. So, each of these triangles, this point is at the center, these sides are at the circle, are on the circle. So each of these heights would be the same, and they would be a radius of the circle. So that's the radius. If you took each of these arcs that would create the bases of these triangles, that would be the circumference of the circle. When you wrap these all around together, that would give you the whole circumference of the circle, which is 2 pi r. Well, the area of one triangle would be 1/2 times b times r. But let's think about how many triangles there are. There are, let's say, n triangles. So wouldn't the area of the circle be n times 1/2 br? Well, if it's n times 1/2 br, this is all multiplication. We can change the order. So let's say make it 1/2 times nb times r. Well, nb is all of these bases together, because there's n of these bases times b. Oh, so nb is just the circumference. 1/2 2 pi r times r. Wait a minute. 1/2 times 2 is 1. R times r is r squared. Area of the circle is pi r squared. This is a very raw, conceptual, idealistic version of deriving the area of a circle. And I hope that makes sense. All right, so area of a circle, pi r squared. That's actually how they developed it, and they were able to verify it later using more mathematics. As more was discovered, they could verify and say, oh yeah, this really is how it goes. But back in ancient Greece, this was how they did it. They were like, oh, look at these. They're basically triangles. As you get smaller and smaller sectors, this arc length is getting closer and closer to the length of the segment that forms the chord there. So they basically would be the triangles. And then they deconstruct it from there. But now we have more to verify that, and you will get that later in your mathematical careers. So that's the area of a circle. If you're finding the area of a circle, let's say you have a circle with a radius of 5. If you want the area, it's pi r squared, pi times 5 squared. 5 squared is 25. leave it in terms of pi unless explicitly told to round, or rounding is what would make sense for the situation. So if you're, I don't know, buying paint and you're trying to paint paint a circle, you wouldn't go to the paint store, just be like, oh, I need 25 pi square feet of paint. You would figure out how much it would take in like gallons or liters or however that paint store measures their paint. And also, don't forget units squared. It's still an area, still needs units squared. All right. So that's area of a circle, but we literally just defined what a part of a circle is called. This region is called a sector. It's bounded by 2 radii and an arc. That's called a sector. There's actually 2 sectors here. If the arc is a minor arc, it is a minor sector. If the arc is a major arc, it is a major sector. I hope that makes sense. But major and minor arcs are not the only 2 types of arcs. There is one other type of arc, and that is a semicircle. And the semicircle is the arc. The arc is a semicircle. This region is not the semicircle. The region is a half circle. The hyphen is optional. I like to put the hyphen, but you don't need it. So the region is a half circle. The arc is a semicircle. So if you're talking about the region and you want to find the area, it will be the area of the half circle. There is no area of a semicircle. A semicircle is not a closed figure. A semicircle is just like that. There is no area of that. It is not closed. That's all the semicircle is. So let's talk about the area of a sector. Well, the area of a half circle is very easy to find. It is half of the area of a circle. And I hope you guys followed with my logic there. Since this is a half circle, the area is half the area of a circle. So it's 1/2 pi r squared. I don't know why I did that so far to the right and not centered. It doesn't really matter though. So that's the area of a half circle. And I hope that makes sense. And if it doesn't, I honestly don't know how to explain it other than that. Now, the area of a sector that's not a half circle we have our radii. So let's say we're finding the area of this sector. This sector is part of the circle. And that central angle is also the measure of that arc, because the measure of a central angle is equal to the measure of the arc. And it doesn't matter which one you're given, because they're the same thing. But if you want the area of the sector is proportional to the area of the circle. So the area of the sector to the area of the circle is equal to, and it is in proportion to, the ratio of the central angle to the entire circle. Or the measure of the intercepted arc to the entire circle. Because the measure of the whole circles as an arc is 360, measure of the central angle the entire circle is 360. It doesn't matter. So this is the area of a sector. Hey, we know a formula for the area of a circle, so we can get rid of this. I know I told you guys not to wipe my boards with your fingers, but I have been washing my hands so much. So it's okay. So area of a sector over pi r squared equals theta over 360. So the area of a sector equals theta over 360 times pi r squared. The central angle over 360, or the arc measure over 360, times the area of the circle. That's how we can find the area of a sector. All right. So that's how you can find the area of a sector. There is one more section of a circle that we're going to talk about. So we have the sector, 2 radii, and the arc. But an arc can also enclose a region with a chord. If you have a region bounded by an arc and a chord, that is called the segment of a circle. So a region bounded by an arc and a chord is called the segment of a circle. This is a segment of a circle. And that's a segment of a circle. Both of those are segments of a circle. And to differentiate, again, it's based on the type of the arc. So if it's a major arc, it's a major segment. If it's a minor arc, it's a minor segment. There is no way to classify a segment when it's a semicircle as a segment, because that is just a half circle. And we already talked about a half circle. A half circle is technically a segment of a circle and a sector. It is both of those things. It satisfies both definitions. It is 2 radii and an arc. It is a chord and an arc. So that's why it's not called a segment or a sector. It is just a half circle. So if it's bound by a chord and an arc, it is a segment of a circle. Each chord divides a circle into 2 segments. And if we want to find the area of a segment, it is very straightforward. Oops. Accidentally bumped into my tripod. Stop wobbling. There we go. Okay. So if we want the area of a segment, well, we know how to find the area of that sector. That's theta as well. And the segment is just a sector with a triangle removed. The area of a segment is quite literally just the area of the sector minus the area of the triangle. That's all it is. That's all you have to do. So let's say this was, say, 72 degrees. And the radius was, we'll say, 12. The area of the sector would be 72 over 360 times pi times 12 squared. Well, 72 goes into 365 times, so it's 1/5 times 144 pi. So the area of the sector is 144 pi over 5. Units squared, that's not my final answer, so I'm not going to bother writing units squared. The area of the triangle Well, there's several formulas that we have for the area of a triangle. There's 1/2 base times height. There's Heron's formula, but we only know 2 of the sides. And then there is the one where it's 1/2 times the product of the 2 sides times the sine of the included angle. So 1/2, hey look, we have 2 sides in the included angle. 1/2 times, times 12 squared, 12 times 12, times sine of 72. I don't know what sine of 72 is off the top of my head, and my calculator is over on my counter, and I don't feel like getting up. But 144 divided by 2 is 72, so it's 72 sine of 72 is the area of the triangle. So the area of the segment, in exact terms, is 144 pi over 5 minus 72 sine of 72 degrees square units. All right, so that's areas of circles and parts of circles. Have fun.